All right, I want to welcome you back to another installment of Math with Medina. Today we're going to look at section 3.3, which is solving equations with variables on both sides of our equal sign. So we start out here, and our very first example is 3x plus 4 equals 8 plus x. And we can see pretty clearly here that there is a variable on both sides of that equal sign. So what I thought might help us out here is to actually kind of highlight that variable in a color to start out. So you can see that the variable terms are in blue, and since those are on both sides of the equal sign, it means that they're really kind of on both sides of the wall between our equation. So it's important that we get them all to one side. So the big question, and if there's one question that you write down in your notes that stands out as a first step, it's that idea of which variable has the bigger coefficient. So I can see that the variable term on the left has a 3, the variable term on the right has a 1, which means that we want to move all of our variables to the left-hand side. And a way that we could do that and show that is we would want to, since the variable on the right is being added, we'd want to do the inverse operation and subtract x from the right-hand side. And to keep it balanced, we'd subtract x from the left-hand side. So now I rewrite my equation, 2x plus 4 equals 8. And now, hopefully, this is starting to look a little bit more like those equations that we were doing in 3.1 and 3.2, where we have to do one or two extra steps here. So the next step of things is I want to isolate that variable term. So remember, that means I want to get this term by itself. And in order to do that, we're going to go ahead and subtract 4 from both sides. And we are left with, at this point, 2x on the left is equal to 8 take away 4 would give us 4. And then lastly, I want to get rid of my coefficient. And so I would divide by 2 on both sides, leaving me with x is equal to 2. Now, once I have my solution, just like we've always been doing, I want to make sure I take a moment and I prove that I'm right. So we write down our original equation, 3x plus 4 equals 8 plus x. Now, the big, really unique thing about these problems is since there's a variable on both sides of the equation, it's really important that we focus on making sure we substitute in both places. So we go ahead and we're going to replace this x, and we're going to replace this x. And if you notice, I haven't actually substituted yet, but one of the things I really like to do on this is I like to put parentheses as kind of a placeholder, or what I would call kind of the skeleton of my equation. And then from here, we substitute in our solutions. We substitute in 2 in place of this x and 2 in place of that x. Then we go through and we simply evaluate our expression. And remember that we want to do it, simplify each side one at a time. So we're going to go through and we're going to simplify this right-hand side. 8 plus 2 would give us 10. And then we're going to want to simplify this left-hand side. So notice, we think about them as two separate expressions, one at a time. It's really important that you pay close attention to those details. And if you have trouble seeing them separately, I might recommend, just like I did with the revealer here and covered up half of the equation, maybe I'd cover up half of it with a post-it note. So 3 times 2 is 6, plus 4, and 6 plus 4 gives us 10. And remember, we bring down the 10 on the right-hand side, and I can see, sure enough, that's a pretty darn good answer. So our solution in this case would be that x is equal to 2. So a couple things I really want to highlight on this before I move on. One is really looking at those original variable terms and ask yourself which coefficient's bigger. The second part of things is really emphasizing that when you substitute on both sides, and then from there, evaluate or simplify each of your expressions the same way we normally would. All right, let's look at another one here together. So we start out 8 times the quantity x plus 4 equals 5 times the quantity 13 plus x. Well, I can see right away that I need to do each of these expressions one at a time. So I'm going to pull that revealer out again, just like a post-it note. Left-hand side of things, I'm going to start out and I'm going to distribute 8 times x, which would give me 8x, and then I'm going to distribute 8 times 4, which would give me 32. Then we move our post-it note to cover up that left-hand side and just the right-hand side one at a time. 5 times 13 would be 65, plus 5 times x would be 5x. So now at this point, we can get rid of our revealer, get back to our normal world, and see our new equation is 8x plus 32 equals 65 plus 5x. And just like before, we're going to focus in on these two variable terms. And this time around, when it comes to those variable terms, I can see again that the 8x on the left-hand side is a bigger coefficient. So that means I'm going to subtract the 5x away and take away 5x from the right-hand side left-hand side of things. And we can see there that on the right-hand side, I'm left with 65. Left-hand side, 8x, take away 5x would give me 3x plus 32. And now at this point, we focus and we kind of hone in on, I want to isolate this variable term. And in order to do that, we are going to get rid of the 32. So I subtract 32 from both sides. And from here you can see we're left with 3x on the left-hand side. And on the right-hand side, 5 take away 2 is 3. 6 take away 3 is 3. So I'm left with 3x equals 33. Divide by 3 on both sides. And sure enough, our final solution, x is equal to 11. All right, so we've gone through. Notice we started out in the very first step of things. We made sure we distributed that number outside of our parentheses. And then I went through and I double checked which of my terms had a bigger coefficient. And that really dictates which side we have our variable end up on. It's not always going to end up on that left-hand side when we're working through our problem. It really is decided by which coefficient has a bigger value. So this time around, 8 was bigger than 5, and we can see now that we want to do our proof. So we bring out our super P, put down our original equation again. 8 times the quantity x plus 4 is equal to 5 times the quantity 13 plus x. And it's really important, and I talked about this in class, that you substitute immediately into the original equation. That you don't distribute anything or anything like that, but you substitute straight away. And we are going to substitute in 11 into both of those. And then as we go through and evaluate things, order of operations says to do the parentheses first. So 11 plus 4 would be 15 times 8 is equal to 5 times 3 plus 11 would be 24. 8 plus 15 would be 120. 5 times 24 also would be 120. So I can see, again, pretty darn good answer. All right, so now let's take a look at a couple more examples, but I really want to emphasize that this example number 3 and example number 4 are what I would call special circumstances, or they're special results as we work through our equation. So we start out this first one. I have 25t is equal to 5 times the quantity 5t minus 1. And remember, we're really focusing in on, I want to get those t's together. So I can see I highlighted that 5 and the t are going to play a special part of this story. So I can start here and I distribute the 5 and I get 25t plus, and 5 times 1 would be 5. It's equal to 25t. So now hopefully something's looking a little bit odd to you because I see 25t on both sides. Well, at this point, let's stick with moving our variable to the left-hand side. So I subtract 25t from both sides of my equation. And on the left-hand side, I'm left with 0. And on the right-hand side, I'm left with 5. So then I step back and say, wait a second, but what happened to t? And I can see very clearly that it disappeared from both sides. Well, now I ask myself the question, and this is a really important question, is this statement true? And your answers would either be yes or no. So I ask myself, is there ever going to be a time where 0 is equal to 5? And hopefully, pretty confidently, I can make the statement, no, it's not true. Well, then what that tells me is that for t, there is no solution. And we'll come back to kind of clarifying the no solution versus the next example here in a moment. But I really want to emphasize one more time that the two things that I noticed is, one, here my variable disappeared And immediately once I saw that, I asked myself this question: is this a true statement? If my answer is no, 0 is never equal to 5, then at that point I know that there's no solution that will ever possibly go in for t that could be true. And in the same turn, if I look at this problem, I have 4 times the quantity x minus 2 is equal to 2 times the quantity 2x minus 4. Well, I start out right away, those parentheses catch my eye, and I say, hey, I see these guys. I know that that means I need to look inside of them. So I look inside and I say, nope, nothing inside there. So then I look outside and I can see pretty clearly I need to distribute. So 4 times x is 4x. 4 times negative 2 is 8. 2 times that 2x is 4x. 2 times negative 4 is negative 8. And I say, all right, this is odd. I got the same thing on both sides. Well, I'm going to keep going. Power through, see if I can figure this out. So I say, all right, let's take away 4x from the right side, and let's take it away from the left side. And from there, I get negative 8. Negative 8 equals negative 8. Something still is odd about this. So I say, okay, let's keep going. So now I'm going to add 8 to both sides. And I end up with 0 equals 0. What? Well, this is actually, again, a special circumstance. It's a special kind of solution. And what happened here, and what really should have tipped us off, is just like before, when I noticed that on this equation, my variables disappeared. And just like before, if my variable disappears, there's a question I ask myself immediately. Is this statement true? And my two options, just like before, yes or no. And this time around, I look at it and say, okay, well, this statement right here, negative 8 is equal to negative 8, that's always true. Negative 8 will always equal negative 8. But if I'm not sure, notice I balanced each side still, and I got to here where I said 0 equals 0, which again, that's also true. If I have 0 of something, that will always be equal to someone else having 0 of something. So I would say, yes, the statement is true. Well, if the case is that I can make the statement that it is true, then what that tells me in this is that whatever variable I pick, the answer is going to be all solutions. And we'll throw the word real in there. We'll come back to that down the road. But all real solutions. All right, so what I want to do now is I want to actually continue with this example and really prove to you what this whole idea of all real solutions means. So I want to do two proofs. First, we're going to pick a random negative number. So let's try negative 3. So we're going to come in here and we're going to plug into our equation negative 3. And as we go through and evaluate it, negative 3 take away 2 would be negative 5. And on this hand, it's 2 times the quantity. 2 times negative 3 would be negative 6. Take away 4 more. Left-hand side of things, I get negative 20. Right-hand side, we say, all right, 2 times the quantity. Negative 6 take away 4 would be negative 10. And I see 2 times negative 10 would give me negative 20. So that tells me negative 3, that's a solution. But here's the thing. Let's pick another number, like 3. 4 times the quantity, 3 minus 2. 2 times the quantity, 2 times something, which we already said was going to be 3. So let's put that in there. And we go through and we evaluate. 4 times 3 take away 1 would be, 3 take away 2 would be 1. 2 times the quantity, 2 times 3 would be 6 minus 4. 4 times 1 would give me 4. 6 take away 4 would give me 2. Odd. And oddly enough, I got the same thing there too that proved it was true. So now I'm confused because I just got that 3 was a solution and I got that negative 3 was a solution. Well, here's the crazy thing. Any number we put in there is a solution. That's why this answer is all real solutions. is it means all real numbers that we put in there, any number we pick, will always make a true statement. So if that's the case, then we can't just say 3 or -3 or 100 or -7, but we have to say all real solutions. All right, so let's write 2 quick rules with this. So we go on, and there's 2 things we want to point out, but the really important thing is you catch this heading that is when the variable disappears. When the variable disappears, one of 2 cases will happen. Either it'll be a true statement or it'll be a false statement. Well, if it's a true statement, that's like example 4 we just talked about, and we said that if it's a true statement, there are all real solutions. That means any number you put in there. So if that's the case, I can't be specific. I have to just say all of them. And if the case is, if it's false, remember we said that there was no real solutions. So in that case, just like on example number 3 we did there, when the t disappeared after taking away 25t from both sides, 0 equals 5 was a false statement, so there was no real solutions. All right, so the only thing I really want to emphasize is this last sentence here at the bottom. Please do not confuse this idea of when the variable disappears as having to do with when we check our answer. Those are 2 very different things. In both of these cases, on number 3, we talked about as we're solving the equation, here and here the variable disappeared. So then we knew it was a special circumstance. Same thing on number 4. Right here and right here, when I took away the 4x from both sides, it became a special circumstance in which I was left with just numbers that were equal to one another. So please be really mindful of this. All right, great. So I look forward to seeing you in class tomorrow. I apologize the video was a little bit long. Hopefully you stuck with me through it, and I look forward to seeing you again.